Hello, I'm Gaurav Barmula, and this is a week 3 of our DSP lab. This week we have to do two things. The first was we have to take a PPG signal, and we have to compute the autocorrelation of that function, and we have to use the property of autocorrelation to find the pulse rate of that PPG signal. Uh, this is a quick summary of the autocorrelation. So this is our formula for the calculation of autocorrelation of discrete or digital signals. So the formula is it is basically this multiplication of the signal by the time delayed version of itself. That is xn into x of n plus m, and n will go from 0 to the n minus m minus n, where n is the total number of samples in the signal. And here we are dividing this autocorrelation summation by r naught, that is the uh, value when m equal to 0. This is called the normalization of the autocorrelation function. uh, if you see carefully, our r naught, at r naught, every value of the function, every value of the signal will be multiplied to itself. That is, it is the summation of the squares of every value of the signal. That is same as the energy of the signal. So here we'll divide the summation by r naught for normalization, and this is a general plot of how a autocorrelation of a signal looks like. So here we see when the signal crosses the zero line for the first time, it is called the zero crossing point. And after that, we can see the signal has various peaks, and the value of the amplitude keeps going down. But the first peak that the signal will have after the zero crossing point, uh, if you find the distance between these two, it will give us the time period of the signal. So this is a basic video that is very helpful in understanding why that distance will give us the time period of the signal. As we see, the autocorrelation is nothing but the multiplication of the signal by the time delayed version of itself. So we can see that these two signals are multiplying to give us this, and we can see that the peak in the signal are when the time delayed version of the signal aligns with its the amplitudes of the time delayed version align with the amplitude of the original signal. So that is why the distance between the peak and the zero crossing point will give us the time period of the signal. So here is a code implementing this. So here this is our signal, this is a PPT data. uh, so first was what we did, we implemented a moving average filter on the signal with length equal to 8. We have discussed moving average filter in the previous 2 weeks, so I won't explain it in much detail, but we we pass the signal through a moving average filter here. Now we'll take the mean value of the signal. So for that we declared a variable mean equals 0 and sum equals 0, and we sum in the variable sum we summed all the values of the signal, and then we divided that all the values of the signal by the total number of samples n of the signal, and that will give us the mean of the signal. As we can see, uh, here n equal to 1000, that is the number of sample. So after getting the mean of the signal, uh, so here we got the mean of the signal. Now we'll subtract every value of the moving average of the signal after passing through moving average filter, and we subtract the mean from it. That is where we're just taking the difference of the uh, output of the moving average filter and the mean value of the signal, and we'll store that in this signal x1. So here we implementing this code. So now we'll move on to the autocorrelation function. So this snippet of our code is for that the submission part of the autocorrelation. So here we'll using two for loops. One for loop I will go from 0 to n, that is the number of samples in the signal, and inside that for loop we have another for loop where j will go from 0 to n minus I, uh, and will sum every value of the signal, that is will multiply that signal, the value at j and the value of at I plus j, and we'll sum all of them for this loop, and then will that will be our value for that instance of I, that will be the value of the autocorrelation signal for that instance of I. But still we have to normalize this, that is we have to divide it by a naught. So here will t float t equal to ACF0, that is this t will store the value of a naught, that is the value of autocorrelation function for I equal to 0, and we'll divide we'll divide every value of the autocorrelation signal, autocorrelation, the output of the after the autocorrelation, we'll divide every value of this by t, that is basically uh, we are basically doing this in that snippet of code, that is where we use two for loop to complete this summation, and then we divide that value by r naught. So here it is. Our ZCP will be our zero crossing point, so we declared it as 0, and now we'll run a for loop over all the values of the signal, and for wherever the signal is such that before that point the value of the signal is greater than 0, and after that point it's less than 0, that will be a zero crossing point, because at that point the signal the signal will cross the zero line, that is on one side of the zero crossing point the signal will be greater than 0, and on the other side it will be less than 0, and ZCP equal to I, that is it will give us the value of the zero crossing point, and then we'll break because we just need the first time the signal crosses the zero line. Now we'll declare two variable lmax and max. So max will store the max will have the maximum value of the signal after the 0 point, and lmax will just store the position of that point, the iterator at that point. So for I equal to 0 crossing point to the end of the signal, that is we are starting this loop from the 0 crossing point. After that we'll see we have declared max equal to 0, and if max is less than ACF, then max equal to ACF and lmax equal to I, that is we are measuring what is the maximum value after the 0 crossing point, and that will be max, and lmax will be the position of that point. We are storing the position of the point of the peak of the highest peak after 0 crossing point in the variable lmax. So now we'll calculate, for calculating the pulse period we'll do this. So first lmax1 we declared new variable, it will be equal to lmax plus ZCP. Lmax is the value of the position of the peak, and ZCP is our zero crossing point. Now to find the period will be this lmax1 divided by 100. So lmax1 divided by 100 will be the period of our signal, and to find the pulse rate will be equal to 60 divided by the period. So we implemented this here. So float pulse equal to 60 divided by the period. So here it is. Lmax plus ZCP will give us lmax1. Our period will be lmax1 divided by 100, and to get the pulse rate we'll divide that period will divide 60 by the period. So now let's first I will comment this. Now we have written these lines to print first our output, our original signal, our moving average filter, our signal after decreasing the value of after subtracting the mean value from the moving average filter, and our autocorrelation function that we have multiplied by 200 just for scaling purpose. So we'll now upload this code.